course called CS 2300 and its lab component CS 2310. And there are like multiple elect courses like Dixis, I guess. Dixis. What else? This one. Forgot. MUP, microprocessor architecture, micro, uh, architecture. MUP, DIGS. There are these two courses. So they teach you about the internals, and then there's also this. These are these four are core courses for CS, by the way. So are the other two for elect. So yeah, these courses teach you the internals of computers. We will cover that to some level, but not a lot because yeah, I'm not trying to make you electrical engineers over here. So now there are two things first of all. One is the processor and the other one is the memory. Uh, yeah. Now the memory is implemented in a very fucked up manner. I have no idea why electrical engineers do that. They just do. It seems they have some thing for making their own lives miserable. In any case, for our purposes, a memory is nothing but a giant ass array. Yeah. 1 unit, 2 unit, 3 units, and so on. Now, each of these cells holds 8 bits or 1 byte. And each of them has an index, right? This is 0. This is some, let's say, 2 GB का जो भी value होता है. So some 2 GB का 2 GB value which is equal to 2 into 10, 2 to the power 10 into 2 to the power 10 into 2 to the power 10, which is equal to a lot. 31. So how much is that in hexadecimal? 2 to the power 4 is 16, 2 to the power 30. Okay, let's say 4 GB. Then this would be 0x 32, 8, 1, 1, 2, 3, 4, 5, 6, 7, 8. I think this is right. Yeah, in hexadecimal. And I would really, really recommend that you get used to hexadecimal numbers because you would be seeing a lot of them. This is what? 16 to the power 3. 15 into 16 plus 15. F is 15, and obviously the place the power value will be 16 in this case. So how much is this? 255. So in hexadecimal, what will be the maximum value of 1 byte? 8 bits, 2 to the power 8, and so 0 to 255. Maximum value, minimum value is obviously 0. So the point is, when memory address of something, the index in this giant array is what we are referring to. And when we say null, it's 0. And we cannot have null as an address because of operating system reasons. More importantly, other reasons as well. But mostly, yeah, operating systems set it as a check for the programmers and for the application. Uh, okay, so the basic idea of binary exploitation is you have the memory, and I'm doing it the other way. You have elements. Now you are supposed in any particular operation you are supposed to access elements only these elements, but you are able to access this, this, this and basically whatever you want after a certain point, which is a very big problem because in between, not every single one of these elements is a variable. Some of these elements are first of all padding. I'll come to why padding, what padding is. But some other things are internals of the program. So I assume you all know how function calls happen. So what's the first function that called in a C program, by the way? Anyone, just say it out. Say it out, man. I can't read the chats every single time.
Main.
Yeah,
Main
yeah, yeah.
function.
Main. Yeah, main. That's right. I mean, there is something else. Let's not go there. Now it can call F1. F1 can call G1. Then F after G1 is completed, F1 can call G2 and F1 can call G3. So I hope you understand how this is going. Basically, the one that's on the right is called after the one that are on the left. So first, second, third. The numbering is also in the same fashion. And FG. So G1 might call H1 and G1 might call H2. Similarly, main may call F2 after that, and the tree continues. You get the point. So now, those of you who have studied graph theory or who will ever study graph theory, which basically includes anyone who takes the MA 300 something course, 3000 something course, 2000 something course, 2130, I guess, will know that this is called a tree. And if you see how the function execution happens in time, you first call main. Now I assume you also know what a function call is. You first call main. Main calls F1. F1 calls G1. G1 calls H1. Then G1 calls H2. So now if I have to draw it on the same tree, and then H1 goes back to G1, then G1 calls H2, H2 goes back to G1, then G1 goes back to F1, F1 goes to G2, G2 comes back to F1, F1 goes to G3, G3 comes back to F1. Now F1 is done with it, F1 goes back to main. Then main goes to F2. Okay, once again, this arrow is muted. So does anyone know what this is called? The way we are going about things?
DFS, depth first
Yeah,
search.
it's depth first search. So in now once again it's not relevant, but I'll just mention it. You go F1, then you do not explore the siblings of F1, the ones that are on the same level. You straight away go to its child G1, then you go to its child H1. Now, of course, there can be loops. That's the point of recursion, but let's not go there. I'm basically showing you what the flow looks like. If you can, I'm sure there would be online animations for what do you call this shit? Yeah, DFS as well. You can look those. So now there is a very particular data structure that we use for this called a stack. Once again, I'm not sure how many of you know stack, but regardless, I will explain it to you. And I will draw it the other way so that you are able to. Now from main, now right now our stack is not empty. We have main. Assume that it is already, as soon as we enter main, the stack is prepared for you and whatever. And main is the first function in it. Then we add F1. Okay. Now F1 calls G1 in itself. We add G1. We add H1. So now this thing of adding one to the bottom of a stack. Mind you, a stack is supposed to grow upward. I'm making it grow downwards for very specific reasons. We'll come to that as well. Uh, this thing is called pushing on the stack. So I'm pushing a function call on the stack. F1, then G1, then H1. Now that H1 is there on the stack, and we are done with H1 now. So we want to go to H2. So what we do is pop. It's called popping. Removing an element is called popping. We pop H1 from the stack and push H2 on the stack. So this so far is clear, right? I am assuming yes. If you have any doubts, just ask me. So far, if anything is unclear to you, cool. So now can someone tell me what happens next once H2 is done? And speak, please.
It will pop both of them.
Uh, yeah, I mean that eventually happens. First, where is the yeah? First we pop H2, then we pop G1. Now what happens?
G2 is pushed.
Ah, yeah, G2 is pushed. G2 gets done. G2 is popped. G3 is pushed. G3 gets done. G3 is popped. Now, obviously, I'm like pushing and popping immediately, but there are instructions that are being executed. Now, G3 is done. Now, F1 is also done. F1 is popped. F2 is pushed, and the thing continues. So, you see how it's emulating our flow, right? The flow through the tree that we showed. Main calls F1, F1 calls G1, G1 calls H1, H1 leaves, G1 calls H2, H2 leaves, G1 leaves, F1 calls G2, G2 leaves, F1 calls G3, G3 leaves, F1 leaves, and then F2 is called. So I am assuming a stack is clear. Mm, okay. So now you saw those boxes, right? The boxes that I drew. Main, F1, G1. So you see these end demarcators, right? They have names. What are the names? We'll come to that as well. Once again, where were we? We were at memory and then we came to function calls. So now let's go back to processor and memory. So I hope memory as an array is clear. Now, oh my God. Yeah, now the processor has various things. First of all, it has an ALU that does arithmetic and other stuff. Then it has an MMU, that is a fancy name for getting things from memory. Then it has something called, once again, they are not as fun as they sound, but we will assume that they are very, very, very simple boxes. Yeah, it's fine. So now we have four general. Okay, first of all, when I said a memory is like multiple units, so each unit is 1 byte. So where do you think 32-bit and 64-bit come from? So if the architecture is 32-bit, the processor register sizes are 4 bytes. So four of these boxes can fit into one register at one point of time. And uh, if it's 64 bits, then it's 8 bytes. Mm, Now, the reason for having registers is, well, first of all, it's the way processors are designed is that they need registers for, well, processing. You need the ALU cannot interface directly with the memory. The MMU does interface with the memory, but its job is to bring things from memory to the registers. Uh, Whatever is there in the processor depends on the registers. So now you may ask, why do we not? Another advantage is they are faster than memory. As in, now that you think about it, we have an MMU and everything is happening from registers. Whenever we need something from memory, we first need to get it from MMU, then load it into the registers, and then the ALU or I don't know whatever else is there in the processor does operation. While if it's already there in the register, the ALU can directly operate on it. So you might think, why do we need memory? The very first reason is registers are large. Like memory is very small. If any of you are interested in it, it's not once again it's not necessary. One bit in memory is from one capacitor plus one transistor. But one bit in a register, one bit in a register, that's an SRAM. Okay, SRAMs are caches. Here it would be. I don't. I think it's eight or six. Six is for cache. That's for certain. Eight or six transistors, and not just any transistors. Like these are simple transistors. These are. I'm not even sure transistors. First of all, like if they can be classified as transistors. Once again, the details are irrelevant. The point is, it's significantly larger than this. Uh, if some elect person cares to correct me, he or she is free to do so. Uh, Regardless, that's not the point. The point is registers are large. That's the first point. The second point, registers are also very expensive to make. So obviously, you can't just shove a bunch of registers in a computer and call it a day. It's yeah, it's basically impossible. Um, so we obviously need memory. Now the stack is maintained in the memory. Those boxes are maintained in the memory. Notice how I'm drawing them of different sizes. They obviously need not be of the same size. To some extent, it depends on the number of local variables. To some extent, it also depends on the compiler. Now there are four computation registers: AX, BX, CX, and DX. If you are on 32, if you are on 16-bit, these are the names. If you are on 32-bit, you put an E, then it becomes EAX. If you are on 64-bit, it becomes RAX. Uh, yeah, and in 64-bit assembly, we'll come to assembly also. You can refer to 32-bit and 16-bit registers. They will just fetch the lower 32 bits and the 16 bits of the value of the register. Have I lost anyone so far? Now is the time to speak. I'll also open the chat in case. Wow. Okay. Anyways, does anyone have any doubt so far? Of what? Everything. Mine. Is it glitching? Someone confirm.
Yeah, sometimes it is.
Uh, See, if you wanna ask that question, I recommend you read Beej and then come back. Uh, yeah, every core has its own set of registers. That's right. Uh, is it unbearably glitching? Yes or no? No. Okay. It's fine.
Actually, like it's difficult to make out what you are speaking sometimes.
Just stop me and ask again.
Okay.
So far, what is not clear? Sounds like a you problem, bro. You can't say nothing, okay? Whoever's there in the session, give me one proper thing that's not clear. Once again, I'll go from the top. You have memory. Oh, cool. Then a memory is nothing but an array. Okay, anyone has any doubts? Once again, I'm being very serious. If you want to stop me so far, now is the right time to do that.
Can you explain the register bits alone, like this last thing alone
Yeah,
again?
so once again, this is not relevant, first of all. So if you really do not understand it even after a second explanation, it's fine. Register, depending on how you make your something called a deep flip flop, which you will study in the courses that are listed above. Uh, register a single register bit. Now, 1 byte is 8 bits, right? So you can store 8 bits. You can store 8 bits in any way. So memory stores it with one capacitor and one transistor. I hope you all know what capacitors are because you all cleared GE. And transistors is something fancy. That's not the point. The point is the number. On the other hand, register bit is 8 or 6 transistors. Once again, depending on how, what, where, when, why, whatever. So these are large. Second of all, they are also expensive because transistors are expensive. So the end point being, you cannot just shove a bunch of registers and say that's your memory. That's too expensive for starters. Second of all, that's too painful. Third of all, that's very, very, very large. That's why we have both memory and registers. And now, because they take 8 or 6 transistors, and it just takes one capacitor and one transistor. Like, just see the numbers. Roughly, you can say that a capacitor is the same size as a transistor. They are very small capacitors, by the way. So yeah, it's see. I'm not explaining computer architecture. It works like that. Like it. So another thing is, this needs to be fed power continuously. This can hold power on its own. Another thing, yeah. So to hold power on its own, plus like the way these work and they are designed, they're just faster. Like you know how capacitors discharge, right? They're slow. They have an exponential decay. That does kick in when you take things from memory. So these are slow. These are fast because transistors can release their charges instantaneously depending on the current applied across them. So yeah, once again, I'm not explaining computer architecture. I shouldn't even have mentioned the numbers. I should have just said they are large, they are small, and packed. Regardless, mm, let me see. Yeah, there's nothing else I can truly say, to be honest. They hold charges on their own. They require energy. So in memory, you need to keep pushing some electricity every now and then to make sure that the memory does not turn out to be all zeros, because that is what will happen if the capacitor discharges, which which is done. That's why your memory takes power. Transistors, on the other hand, they do not lose their charge, so registers can hold their value for a longer time. Once again, now we have four computational registers in the processor. The memory is not required. So A, B, C, and D, very conveniently named. Ignore the X. R, you can keep it if you want. R is 64-bit, E is 32-bit, no prefix is 16-bit. Later, sometime later, I'll also expose you to 8-bit registers, but that's not relevant because there was 8-bit architecture. Yeah, nobody's using 8-bit architectures. Uh, so these are for computational registers. Uh, we have an instruction pointer. Yeah, I think that's the name in x86. So 16-bit. This is special. We'll come to why it's special. Similarly, EIP, RIP. This is very, very, very special. The end game depends around it. Now we have two more registers, SP and BP. These are called stack pointer and base pointer. Now, you might have realized that these are what demarcate the stack frames. So, the boxes of each function, this is the full stack. Each box is called a stack frame. Uh, the Now this is higher memory address. So 0 is somewhere here. High memory address is somewhere here. So this is 0x how many ever f's, and this is 0x0. So you remember these are the indices that we have in memory. The memory being a large array, these are the indices that we have. So this is how a stack grows. Now a stack does not exactly start from 0xFFFFF. It starts from somewhere in between. Once again, the details are irrelevant. The point is it starts from somewhere in between. More often than not, you won't even know where it starts from. Neither does the kernel, the operating system, neither does the program, neither does the programmer. Nobody knows where it's starting from. When I say you, I mean the attacker. So this is a stack frame. Is this much clear? Hmm. Cool. I'll just keep it here so that I can also see your chats. Now there is a lot of stuff that's happening around the stack frames, and our entire business also happens around stack frames for now. Now a stack frame just holds the variables of the current function. So let's say in this short program, there is only one variable s, right? So how many bytes do you think it will take in the stack frame? Hmm. Bytes. Yeah. Uh, okay. As it turns out, it takes 16. We will come to sometime, yes, padding. We'll come to why padding, what is padding, and why, just why in general. The long story short, the compute, once again, I'm not teaching computer architecture over here. I am by no means an expert in computer architecture, first of all. So, like, don't even expect me to give you a very accurate explanation. Point being, your 8-byte chunks, 16-byte chunks, so basically, yeah, this much 8 bytes, 16 bytes, they are accessed more efficiently than, let's say, 5-byte chunks. In general, when you want, as you saw, the registers are either 4 bytes or 8 bytes. When you want to do a 1-byte operation, you'll still get 8 bytes from your memory, load them into the register, then operate in such a way that the remaining 7 bytes, something happens to them, you don't care. But the 1 byte has that operation that you wanted. Now note that this is happening in the register. The memory is still like that. Then when you write back from register, only that 1 byte is written somehow. Basically, you have 8 bytes, add more boxes. 1, 2, 3, 4, 5, 6, 7, 8. You have 8 bytes in memory. Now you want to get, let's say, this byte, this particular byte. Now, what you do is you get all of it into registers. 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. You get all of it into registers, into one register. Let's say you got it into RAX. Now the this is 0, this is 7. So you wanted to operate on the third byte. You wanted to operate on this. Let's say you wanted to change its value to B. Right now it's what, 24. You wanted to change it to 25. You add 1 0 0 0 0 0 0. These are like byte values. Don't take them as decimal values, please. So that's what you add. And then you write this back to the same location. That's how a single byte is changed. So, long story short, it will always happen in 8 bytes, 16 bytes, and so on. 16 byte being a requirement by the operating system in most cases. Once again, that is because I lied to you right now, and I'll tell you the truth later on. There is not just a memory and a processor, there are more things in between, and they once again they prefer 1632, stuff like that. So the operating system, yeah, integers are 4 bytes, and you have two integers in one 8-byte chunk. Yes, integers are 4 bytes, but like I don't see the problem. They You work on them similar to how you work on a single byte. Once again, if you have to, so yeah, if things combine to form 8 bytes, you can combine them. Let's say you have 1 byte character, one integer, and then three characters. Like this is how your memory is laid out. This will all fit into one like 8-byte chunk. Each of them, it's not like this will have 8 bytes, this will have 8 bytes, this will have 8 bytes. That's not happening. All of them can fit into one 8-byte chunk, obviously, because like it's nonsensical to the way we are doing operations. It's obvious that it's nonsensical. So yeah, your stack frame holds your variables. So what are the two parts of a program? High level thinking. One is variables and the other is, like, you have variables, but variables by themselves are useless. So in a stack frame, you hold variables. Where do you store what to do with them? What is that, first of all? Yeah,
Instruction.
instructions. So in this case, what are the instructions? Now, char s of 10, that is also instruction. That is instruction to say there is a variable of called s with 10 byte space. Now this is an instruction, this is an instruction, this is an instruction, this is an instruction, this is an instruction. This is also a function call. Long story short, program, the way you write is both instructions and variables. So your stack frame just has instructions for now. Any general program in general will just have instructions. So you have now, as I told you, there is a memory of an array. Okay, instructions, the part about instructions, fine enough. So this is an instruction, right? This is what is this doing? You studied Beej, I'm assuming, or you all know C programming. So what this is doing is set particular byte indexed using I to the character A. That is an instruction. That is, there is no, okay. There is, you're not creating a variable over there. You're setting a variable. So this is an instruction, right? Harsha, I'm assuming that's clear. Yeah, okay. So now this is also an instruction. This is an instruction that expands to multiple. This is a function call. It expands to multiple instructions. So yeah, C to instruction mapping is not one to one. I'll show you what is a one to one mapping to instructions. Let's see, either today or mm, what is the time? 3:45. Okay, probably some other day. I doubt I'll be able to cover that much. In any case, so you had memory, right? Hmm. Now you divide the memory into segments arbitrarily. There is a very well defined logic on how this is done. Once again, do not worry about that. Assume it's done. You have a section for stack and it's fixed by default for most part. Once again, it depends on the OS. Assume it's fixed. Uh, your stack frames grow like this. This is once again higher memory address. Keep this in mind. The higher memory address comes up. This is a convention. And now we had instructions, right? That's stored somewhere lower in a segment called code or text. Keep these names in mind. They will be very important. Now, if you have, okay, you all have heard of malloc. That's not the point. The point is it's not there on the stack. We'll come to where malloc stores stuff. It's heap. I'm not going there. If any of you misheard it, it's heap. So yeah, stack, code and text. Function calls. See, there is a lot of stuff happening in function calls. We'll come to what function calls are exactly doing. Okay. So now the code section stores instructions. Now each line in this is an instruction. Do you all remember IP, EIP, RIP? I'm working with 32-bit for now because things are easier in 32-bit, which is why 32-bit is also more exploitable. Uh, EIP is if you remove the E, which is for 32-bit, the IP is instruction pointer. Now I think it's very obvious from the name what instruction pointer does, right? Okay, once again, any doubts so far? Now's the very good time to ask. See, I'm going very slow, by the way. Like, if you ask the coordinators, they started crying when I took the first few sessions. If you have any doubts, feel free to raise your hand, put it in the chat, just unmute and ask. That's also fine. But please ask. No, no, no. So once again, stack, this is the stack grows this way. So if there is no top boundary, stack grows this way. See, ideally, it doesn't make sense. Like, what is a stack of plates? You keep plates on top of each other, right? Now you keep a plate on the top and you do not insert it at the bottom. So you keep a plate and then you keep another plate on top. So it grows upwards because of gravity. But here I am doing it on a very specific purpose. Stack ka bottom is at the higher memory address. This is the bottom. This is the top. It grows down to lower memory address. Clear? Harsha? Karthikeya? I am not sure which one is your name actually. So sorry. Where? No. See, uh, did I? This is the code section. Just to be very clear, this is the code section. This is full memory. Let me go up. This was stack frames. This is I don't know what this is. You don't need this. This is one stack frame that had variables. Uh, yeah, this is 8 byte ka chunks. This has nothing to do with stack frames. This is just I'm telling you, stack frames will always be 16 byte sizes, and things will always be things will always try to align themselves to 8 byte ka sizes. Uh, yeah, this once again I have no idea what this is. Yeah, so over here, right? It starts from some arbitrary process. See, higher address on the top, zero on the bottom. Stack grows downwards. I think even then I kept drawing it downwards. Yeah, I don't think I would have done that, done it wrongly. Like I've done it for many times. So yeah, this is clear, right? Cool. Now each line in the code represents an instruction. So what does EIP do? It points to the current instruction first of all. Once this is executed, it moves to the next instruction. Now some instructions like jump, which is represented by J, followed by a relative address. So let's say J minus 0x1. What do you think it will do? I'm adding a minus sign, but like it's actually 0x. There is a way to represent -1 in hexadecimal without the minus. We'll come to that as well. Go down. Stacks bottom at bigger address are when? Okay, yeah, bottom at bigger address. Yes, because that is the way I'm drawing it. It is That's
No, so
how I
in
am.
computer, how does it like? How is it done?
It doesn't see computer does not have like plates inside its processor or memory. Okay, it's just that this is an abstraction. Once again, this is an abstraction. Actual things have something happens. Doesn't matter. Okay, but like what the way I am showing it is because there is a reason for this. FF is on top. This is on bottom. This is a natural hierarchy of numbers. Larger number on top, smaller number on bottom. Stacks bottom is at the higher address. The reason I call it bottom is because that's the one that's not changing. The top is the one that keeps on moving. Sriram, is this clear?
Yeah.
Cool. Move IP 2 bytes back, not two. So yeah, it does what Rishit wrote, move IP 1 byte back and change. No, it does not change. Jump is relative. Okay, it might be absolute also actually. I'm not sure. Long story short, my intention was to say go here. So go here. Then next instruction, it will execute, it will come down. It will again go up. So this is an infinite loop. This was just an example. I actually don't know. It might be absolute as well. Abizar might be right. I'm not sure. The point is J makes it jump. Now, where is this J? What is this J? Doesn't matter. It's an assembly instruction. We'll come to actual instructions. For now, understand what EIP is doing. Each line is an instruction. It goes, it's here, then it goes down. It can go up if you want. It can go more down than one, just one if you want. If like I did not extend the code section, I just like this is the code section. It can go down, it can go up, it can go wherever you want it to go. Okay, top to bottom. Once again, top to bottom. Okay, uh, I'll draw it and like once no the other way, which is why I drew stack the other way because so this is the first instruction and you move down 0x0. No, like this is in general something I should have cleared. Thanks, Manu, for pointing it out. Thanks. Uh, so you EIP moves this way. Stack also grows this way.
Actually, I have a bunch of doubts.
Just ask
Code
off.
block,
It's fine. Huh?
can I ask now or later?
Yeah, just ask off, ask off.
Yeah, a code block is something that is fixed, right? It's not going to change during runtime, right?
No, for
So,
now.
okay,
For
fun.
now, assume it's fixed. See, a lot of things will be like, what the fuck if I just dump them on you? That's why I'm going one step at a time.
Okay, and code runs from like bottom to top, right? Normal stack kind of thing, right?
No, 1 second. I don't know what is your bottom and what is your top.
My
So
bottom is 0 and top is higher.
no, it goes from higher address to lower address.
Okay,
So
just
if
like a
this is
stack grows.
yes. So 4,000. This is a number I pulled out of my ass. Don't There is no special significance to this number. Once again, there is no special significance to this number either.
Okay,
Both of these numbers are something I pulled out of my ass. Do not remember these numbers. It goes from 0x8000 and downwards.
okay, got it.
Any other doubt? You said you had a bunch.
No, this cleared everything.
Okay, please. So this is the code section. That was the stack. Hmm. Now code stores instructions. Stack stores. Stack frames store variables. So now there is one instruction called call. It takes the name of the function. Where are the pointers stored? Which pointers? The pointers are registers. You mean RIP and all? I know. Yeah. So those pointers, if I remember correctly, I did write them above. Yeah. These are all registers. They have they are registers. Processor takes values from here and assumes that they are correct. Our job is to make them incorrect or correct to our own liking. So now let's say we are at main and we call F1. Okay. As I said before, EBP and ESP demarcate. This is the higher address 0xFFF 0x0, and this is main. Okay, I'll actually shift this a little bit down. So ESP and EBP. Okay, now for clarity's sake, I am drawing code section separately over here. I hope this that you are clear that it does not mean that code is somewhere else entirely. Like it's still in the same memory. They are in the same memory. And these lines indicate instructions. Now there is a call instruction. Okay. So call F1. How it figures out F1? Not relevant. Long story short, call has some information about where what it's calling. Okay. I'll explain all of this in detail eventually, as and when the time comes. So now we have to make a frame for F1. Okay. 1 second. Yeah, sorted. Uh, so now let's say we just make a frame for F1. So now let's say F1K instructions started somewhere over here. These were all light lined. F1K instructions. You can turn on your cameras by the way if you want. I'm on not lab, accommodation Wi-Fi, so it's pretty high speed for me. From my end, there would be no issues if you. In fact, I recommend you all turn it on. So let's say if F1K instructions start from here in the code section. So that's actually what call is. Call is storing. Call knows that this is the offset to F1K instructions. So call. So what do you think call does? Now this is EIP over here. Jump. That's a good guess. Now let's see why it just cannot jump. If it just jumps, and then when you are done with F1, how do you think you'll come back? Because as we said, after we are done, we have to come back to the next one at least, right? Store where we are and then jump. Yes. It gives return position along with jump. That's also true. So call does both of these things. It stores. So it gives return position means it stores. So this was the current stack frame of main. You so currently EIP value where at call was EIP1. Once again, there is only one EIP. I'm marking variables over here. EIP1. Okay, it stores that over here because it obviously cannot change the code section as Manu rightly pointed out or asked, whatever. So, and then it jumps to F1. It's also the same as EIP. Now execution happens. Now there is as there is a call, this is called this. Let this be EIP2. There is a ret. What do you think ret does? See, there's a reason I'm asking this. Yeah, goes back to where it got called. Yes, yes, yes. To the stored value. How does it know where's the value stored? It's somewhere in the stack. This is all stack. Can you avoid bottom right corner for right? Oh, bottom. Okay. You mean the ret is getting cut off? I'll scroll it up. Yeah. Okay. Is this visible? Yeah. Okay. Uh, right. Okay. I'll keep that in mind. Thanks for pointing it out. So remember how we said, okay. Okay. There is a ret. So EBP is here. ESP is here. right? So when EIP has to uh, when EIP does a call, basically when a call happens. So initially there is no EIP one and next stack frame isn't there at all. Call is not concerned with the next stack frame. We'll come to why. Uh, now it has to now the call stores EIP one, right? At the same time, ESP is moved from here to here. So the main ka stack frame is still this much only. When something is parsing through main, what do you mean parsing? So see, once you compile the code is gone. There is only instructions, there is only a stack for now. Once again, for now, please don't kill me later on. Uh, Point is, there's a call that happened. The call happened. So in main, okay, I'll show you here. You all can see the code, right? So this printf, this is a function call. So what it will do is go to printf, assume it goes to printf. Library functions are handled differently. When this happens, so in the instruction format, it will be something like uh, call printf. Forget about arguments, forget about everything else. This is what happens effectively. Kartikeya, I am assuming this. Okay, cool. Arguments, will come to that. See, right now it's very, very, very theoretical of sorts because, like, I do not want to just dump things on you all at once. I tried that with coordinators and they clearly did not like it. Uh, and plus, like, I think this way it's better for you to understand what's happening. So now ESP points to return address. Okay. Now let's say you have a function. So do you all see what happened over here? What's happening over here? Uh, so forget main, ignore main for now. Main is special. F has only F has only one, that is to call G. Does it have any variables of its own? No, right? So do you think it needs a stack at all? No, yeah, it does. I'm assuming Abhiram's no was for stack. I'm assuming I got your name also right. Uh, so yeah, please feel free to interrupt me if I get names wrong. I'm so sorry. I'm from Shimla. I have no concept of like how Tamil or Telugu names work really. I'm really sorry. Bro, half of the time I'm confused in Japan. Some of them use first name first and some of them use first name last. So yeah, it does not need a stack frame, but this business of call will happen. Okay. So now do you think who do you think should prepare the stack frame? Uh the function or the instructions? Okay, it doesn't even make that question doesn't even make sense actually. But if main calls f, yeah. I'll correct myself. I'll correct myself. Yeah, what Abizar is trying to say is what I was asking. If main calls f, does f prepare its stack frame, or does main prepare f's stack frame? What do you think? Who has more knowledge of the function being called? Main. Sriram, why do you think main will prepare it? F. Yeah, why do you people think F should prepare it? Okay, it's not a question of will or should. It like will. It's a question of who
Main
should prepare it.
main also knows where to return it back. If just
That's fine, but
knows where,
that's handled by ret and call, right?
yeah,
What if F never returns back? Main will only move the pointer. Yeah, that's right. What Vibhu is saying is right. No, what Rishit is saying that will give any args if needed. We'll come to arguments. As I said, we'll come to arguments. Assume there are no arguments. In fact, in the functions that I wrote, there are no arguments. So yeah, Abizar, I'll come to your point eventually. Hopefully before 8. There are 20 minutes left. So that's right. People who said F, that's right. And Vibhu's explanation is also right. Main will only move the pointer. Main will only do the call. So now, then F creates its own. Pretty much. We'll come to what initial state is, and we'll come to what F's state is. Uh, Main EIP1. After F, we return here. Return here means return to this value. Now F calls G. EIP2. After G, return to this value. Okay. Clearly, main is not preparing the stack frame for F. Clearly, F is not preparing the stack frame for G. Who does that? F's stack frame is prepared by F itself. So now, every if F needs a stack frame, F will have something like this. If F needs a stack frame, the if part is very important because in this case, I'm not compiling it and showing it to you, but F will not prepare its own stack frame. Uh, uh, G का first instruction will be push EBP. So right now, currently, yes, uh, yes, EIP2 is the current EIP. No, right, no, wait. EIP, see, F will have something like, okay, no, EIP2 is not the current EIP. Nisarg, let's clear that first. So F, I'll 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 manually explain to you what F will be something like call G, ret. Call G happens. This is EIP2. Then once this is called, this is stored. It doesn't matter. This is stored. This is stored. The long story short, this will be where execution happens from next. So you can say EIP2 is this. Hmm. Let's do it this way. This is what EIP2 is. So once you're done with G, EIP2 will be the EIP, and then RET will happen. In that case, EIP1 will become the EIP. Is that much clear? Nisarg, what is EIP2? Fair enough. I added three functions. Uh, the immediate next instruction of call if is EIP1. So we are not here yet. EIP was here when call happened. Call stored this value on the in the stack wala region where I showed you. EIP1 clear to everyone? Okay. Now this is main. I'll label it. Crap. I forgot to record. Sad life for those who did not attend. Is anyone recording personally? Just say yes, please. Fine, light. Now F is just a two-liner. So this is EIP2. When EIP comes here, it sees call G. Okay, EIP2 will be stored, and then we go to G. Nisarg, is EIP2 clear now? Cool. So now we'll come to how G creates its stack frame. We'll come to arguments also, by the way. Where is EIP1 and EIP2 stored? Okay. Mm, I'll cover both that and the next stack frame creation together. Just hold on for 5 more minutes, Manu, I guess. Five should cover it. So we have main, stack frame, EBP, ESP. Fine. EIP1, yes, EIP1 is for F and EIP2 is for G. Wait, what? No. Matlab, you mean call, right? EIP1 is the instruction pointer moving along main, EIP3 moving along G, yes. EIP3 is the current EIP. What Vibhu is writing is perfectly right. EIP1 is the instruction pointer moving along main. As you can see here, I don't know why this is glitching, to be honest. EIP1 was the one that was moving here. Call happened, so you stored the next EIP1. EIP2 was the one moving along. EIP1 is currently pointing to F, right? What is F? What do you mean by F? Okay, F, this F or this F. EIP1 points to the one after this. This is EIP2. When F function, no, bro, I mean, okay, F function, I'm assuming this is F function, this is F call. It is pointing to F call, or to be more accurate, the one next to it. EIP2 points to G call, or to be more precise, the one after it. EIP3 is somewhere is doing some bullshit in G. What is that bullshit? We'll come to it now. Because G has to create
A
its stack.
small doubt.
Go on.
Like, what do you mean by a stack frame of a function? Is it like the commands part which you told, or is it something else?
See, you remember the stack, right? The stack frame that stores the variables of the function.
Okay, yeah, the variables part. Yes, fine.
See, the code part is fixed. Khatam. That is not changing at all.
Okay.
Usme, you have instructions for main, instructions for F, and instructions for G somewhere. Abstractly thinking, so if there is some function call in G as well, let's say H, then we will have EIP4. Yes, that EIP4 will be the one that is going through H. Arush is right in this one. So, and in that case, in fact, that EIP4 will be the printf because we have a printf call. Once again, I'm not showing you the printf call. Please do not ask me how printf calls work right now. If I tell you, you will give up. But there will be an EIP4 moving through printf. Right now, we only have EIP3 that's moving through G. Assume that printf call magically happens. So this is clear, right? This is stack. Is everyone clear on stack and heap? Stack and code.
So like stack of a function only stores its variables. Is that correct?
Yes,
And the code part is there in some other separate place, whatever it is.
in memory, once again, memory stack. Yes, you see, stack has its own thing, code has its own thing. Where is EIP1 and EIP2 stored? Yes, Manu, I'm coming to that. I'm coming to that. That was what I was going to cover. So it's stored in stack, more precisely between stack frames. Main EIP1, when the call to F happens, as I said before, it stores EIP1 here. This is happening as soon as call F happens. EIP1 gets stored here. ESP is moved down, and EIP and EIP2 begins. Manu, so far clear? What if main is not over and main stack frame is not fully constructed? I haven't covered how stack frames are constructed. Wait till G. Probably 5 more minutes. Yeah. So now EIP2 begins. Now EIP2 encounters a call. EIP2 is stored. Now once again ESP is moved. Okay, I think I'm writing to the bottom right again. ESP is moved down further. A call G happened here. Now, how EIP1 and EIP2 are stored, is that clear to everyone? Then I will come to stack frames. Is there only one EIP? Is there only one stack for EIPs? No, no, there is only one stack in total. EIP is stored in between the stack frames. Please repeat once more. What part? One second. First of all, Vibhu, what do you mean? Do you mean separate stacks for EIPs and stack frames? No, no, no. There is only one stack. 8 bytes for each pointer. In this case, 4 bytes because it's once again, Arush, I'll come to you also. 8 bytes. No, this is 4 bytes. EIP. 32 bits. Okay. Okay. Arush, coming to you. Repeat once more. Okay. Call F. ऊपर 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 yes और ऊपर EIP1 encounters a call F. The next value is stored here and ESP is pushed down and EIP2 begins execution. Arush, is that much clear? एक call में all of this is happening. EIP1 is stored, ESP is moved down, and EIP2 starts. It hasn't started. It starts in the next instruction. Okay. Now it says it sees call G. Once again, the same thing happens. EIP2, more precisely, this one is stored. ESP again moves down. EIP is the one going to the commands part. Yes. I think you're not making notes. I think you people are not making notes. There's no way you would have had those doubts. So if old base pointers are stored in the stack, Abizar, I'll come to base pointers. Hold on.
So after the stack is like uh, over, like our thing is done with that particular frame, the ESP has to jump back, right?
ESP. I will come to that as well.
Okay, yeah.
I that happens in RET. I will take care of that. RET will take care of that, to be precise. Okay, guys, are you all okay if this extends for like 15 more minutes? Make things, but things are shuffling tough to make notes. That's fine. Okay, I'll extend for 15 more minutes. I'm so sorry, but like there's no way I can finish it in the next 5 minutes because you will just mess up everything otherwise. Uh, yeah, I should have recorded. Some from the next session, someone please explicitly remind me to record things. I'll forget otherwise. And I had to send it to people. Anyways, yeah. So as Sriram asked, ESP has to move back. It will move back. If I come to ret, it will definitely move back. Okay. Okay. Actually, let's say G did its business. No, 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 no. Okay, I'll come to G. I'll go in the sequence. So as Thirukilash pointed, 4 bytes. Yes, 4 bytes are stored here. 4 bytes are stored here. Okay. Uh, now what? 32 bits. Yeah. G G has to create its own stack frame, right? It has one variable. What does it do? So the very first instruction is push RBP, push EBP. So now things are going to get messy, very messy. I'll take a full fresh page. Rather this, yeah. Now we have multiple EBPs as well. EBP1 main. Okay. EIP1, EIP2. You all remember where they came from? I hope you do, because in case you don't, revise your notes so that you clearly did not make. Just kidding. I'll okay. So this one is continuing in main. This one is continuing in F. G ka is currently in the current EIP. That's the one that's running. So we don't need to store it anywhere. ESP is here. Now push EBP happens. EBP1. Do you understand what happened? It did nothing but store the value of EBP, the current EBP, and pushed ESP down by 4 more, by 432 bits. I'll send this as a PDF, by the way, so don't worry about that. Definitely, that's not the concern here. Why push EBP? Why push EBP? Very good question. That the first instruction was push EBP. Okay, hmm, hmm, GK instructions. Push EBP. Remember how I said EBP and ESP point to the current stack frame? What is the current stack frame? The one that G is creating for itself, right? Manu. Yeah. So now the next instruction happens. Mark this as EBP2. So if you just replace EBP with the new EBP value, how do you go back to the old stack frame? You can't, which is why, sorry to ask, but I forgot what EBP does. EBP points to the base of the stack frame, ESP points to the growing section of the stack frame. Okay, Arush, I am assuming that's clear. Yep. So now Manu asked, what if main stack frame was still growing? Long story short, by EBP2, do you mean the new EBP is created or is it the modified value of the initial thing? So why is EBP moving? Because a new stack frame is being created. So stacks are nested inside each other. Nested का मतलब होता है? I'll come to that. So yeah, Manu, please hold on a little bit more. I understand that doubt. If main stack frame still has to grow, right? Long story short, it cannot grow. It is not allowed to grow. There is no chance for it to grow. It won't grow because so you while compiling, you already know what the functions are. And let's say if there was mm, let's say so now there's a third variable that you introduced. It does not matter if that variable is going to be used or not. There will be space for it. So over here, how many variables there in total? Do not see if, else, for, while, anything. Just tell me the number of variables. Once again, I can't see three. Yes. So what is the size of an int, people? 4. What is the size of the stack frame of G then? Why 8? 12, 12. There are 3 variables. Do not see if it's true or false. 16. That's right. 16. Abizar is right. Manu is right. Vibhu is also right. 16. Adding. So where are we? In move sub ESP 0x10. This is 16, yes. Now there is a shadow value. We do not need to store it. There is a reason why. It's very smart. This is a shadow value. So space is reserved for all future variables before the function call. Yes, that's exactly right. That is what is happening here. So EBP, call it EBP2. Long story short, it doesn't matter. So with this, a new stack frame is created. Are we clear with the stack frame creation part? What if there is recursion? Doesn't fucking matter. For recursion, function call is just the same as another function call. It assumes, okay, so the part where we first need to store a variable for function will make stack if main had args, stack if no args. Once again, I had never come to args, but if I can't, I'm not even reading all that. Okay, Okay, so the part where we first need to store a variable for a function will make stack. If main had args to give it, it would make stack. If no args and if no main will never make FK frame. See, I wish I could teach you stacks, but like that will take another 15 minutes. Please try to like how you EBPs and you will give up, bro. Trust me, if I do that, no, you'll give up. By EBP2, do you mean the EBP2? Do you mean the new EBP or is it the modified value of the initial thing? See, there is only one EBP. When I say EBP1, this is a value. This is also a value. There is only one EBP at any given time. Right now, EBP1 is stored. EBP2 is the one that's being used. And these are values. EBP register only one. The register, there is only one register. See, that's the entire point of storing EBP1. If you overwrite it, you have no way of going back. You said ESP is growing part, but EBP is at end. I mean, see. Oh, shit. Sorry. Thanks. My bad. Thorat, thanks for pointing it out. ESP. Thorat, I don't know. I hope that's clear. And yeah, cool. Sorry, my bad. That was my bad. So there's a shadow value. We do not need to store it. We will come to why. So now you remember sub ESP10, right? So now function will do its thing. G will do its thing. It has some computation. It has some arithmetic. It has some other function calls. All of that does not matter. What matters is when you come to the end. So now you have, what do you think this is doing? Anyone? Put it in the chat or speak it out. Go back to the start of the function. Yes. Set EBP at current ESP. Other way around. ESP at current EBP. Go back. Yes. See here. No. EBP to ESP. This is ESP to EBP. Manu, I think you messed up the order. So this is like the CP command or the MV command. Clear? Manu, I hope that's clear. ESP gets written as EBP. So yeah, so when that instruction gets called, this goes back to ESP1. Now ESP1 is no longer, congratulations, ESP1 is again the current ESP. Manu, is this clear? Okay, what part are you getting confused? Like unmute and speak.
Um, ESP gets written as EBP, like ESP moves to EBP, right?
Yes, so it was initially here. When the move happens, ESP is now back to where EBP2 is, which is also where ESP1 was.
But ESP1 was never stored.
We don't need to because EBP2 is already there.
Yeah, okay. So after this, if something happens, it is overwriting.
What? To ESP, yes. Okay, after this, there's only one thing that can happen, by the way. I'll come to that. So, do you all remember this push? And then yes, pop, Rishit is right, EBP. So, this is nullified by this. So, pop EBP it moves the value of EBP1, which was stored at that location, to ESP, to EBP register. So EBP continues execution from here now. ESP at the same time also moves up. Itna clear to everyone? The stack frame is gone. G's stack frame is gone. That's how G's stack frame is created and destroyed. All of this is happening within G. What the fuck? Huh. So is this much clear? Oh, so are we storing IPBP except in the caller stack frame and not the function call? Not the function that is called. See, the way I prefer to say it is that they are stored in between stack frames. You can say they are stored in functions parent stack frame. You can say they are stored in child stack frame. In my opinion, it does not matter. They are stored in between stack frames. As I said, EBP1 was here, G was here. Abiza, is this clear? It makes sense. Okay, makes sense. Okay, cool. Nice. Now, do you all remember that call that happened somewhere back in F? Yeah. Do you all remember call G that happened here? Damn. I think I was too intense for him. Uh, so now G has a ret, right? G also has a ret at the very end. Ret is return. So do you remember what call did? Call added the EIP here, shifted ESP by down, and moved EIP to the function. Ret does the exact opposite. Moves ESP up. This, so now it goes back to EIP2. So EIP2 was in F. So EIP now EIP2 will continue execution. Could you explain again what pop did, bro? What do you think? What this it read? See, if you have a doubt at something, just ask it then and there, because like I erased all of that. Okay, so this is ESP. Assume it's somewhere. Long story short, if you do push some value, so right now we're pushing EBP ka value. What it does is stores EBP. ESP points here now. Push is clear, right? Push is clear to everyone. Can you all? Okay. Yeah. Pop. Pop does the exact opposite. Pop EBP. Take this value. Take this value. Move it to EB. Move it to EBP ka register. This is in memory. This is in. This is a register. And then move ESP up. So these two undo each other. All pops right to register. Yeah, the register that you specify here. Yes. Manu, this clear? Does pop know that the value is popping to EBP, or is it in general? See, the the instruction had pop EBP. So the instruction knows that the value has to be popped to EBP, because you said pop. You didn't just say pop. There is no pop alone. There's a pop followed by some register ka naam. It could be pop EAX also for all that I care. Nobody just does it. Okay. So pop followed by the register is where the value is popped. Uh, cool. So pop and write to register is pop reg. Yes. Yeah. Okay. I see what you mean by pop. You by pop you mean move ESP up. And yes, pop and write to register. That's I think that's what you mean, right? Yeah. Yeah. Cool. So push and pop. Harsh, Karthik, are they clear? What do you mean? What do you mean? Do you all remember back when I told you about processors and memory? They are separate from memory. So right now it's in memory. This entire time I was dealing with memory. Here is where EBP1 was. You write that back to EBP register. EBP register was currently here. When you do pop, it goes here. Because why? The value was written to the EBP register. Harsha, Kartikeya, Otukuri, CS24B075. Is that clear? Cool. Like, just unmute and speak, bro. I don't have time to, you type very slow.
Like, I mean, when you said write to the register, you are saying that the EBP will go back to its original value, like where it was
Yes,
initially.
yes,
So,
yes.
like, my doubt is when you how you bought an EBP one by saying like pop and you got it in the stack. So
Push.
when you
You
are
you did a
saying,
push.
yeah,
Wait.
sorry,
You did a
yeah.
push.
Hmm. So then after that, when you're trying to pop, like you're going back to the position where EBP zero, like the initial EBP was present.
That
Is
was
that right?
EBP1 ka value. See,
Okay,
EBP1
so
was this. EBP. Okay, one second. EBP1 was this. You did a push. EBP1
okay,
got stored here. EBP1, like EBP is still at EBP1. Then you did a move EBP to ESP. It
okay,
basically became an EBP2.
okay,
Now what's the doubt?
okay. Okay, so by writing it back, you mean that you're giving it back the original address or something?
Yes, the original address to where it was pointing.
Okay, okay. I guess I understood. Fine. Thank you.
Cool. Uh, where were we? Ret. Did I cover ret? Did I start covering ret? No, I don't even remember. Anyways,
You
ret.
told it's the opposite of call.
Yeah. Okay, it's above. Yeah. You come to ret. Ret undoes this call. What did that call do? Where was the? Oh yeah, that started when he asked what is pop and push. Okay. So you had EIP2 here and ESP here. Clear? Ret basically means read whatever is the value here, and EIP continues execution from there, which was when we come back, EIP2 was this line. Ignore whatever is written here. Any doubt in ret? Ret is very simple. Hmm. Perfect. Ret does that's pretty much it. See, the reason I will. Mm, yes, Manu is right. Effectively, that's what Ret is doing. We just not write it that way because we cannot. There is no way on earth you can pop something to an EIP. You have to do a Ret. Why do you think that is? That's because EIP is special. Whatever EIP points to, it starts executing. So you can basically get a lot of things, nasty things done. Ret moves ESP up. Yes, Arnav is also right. So EIP2 goes to ES EIP. EIP continues execution from EIP and ESP. That's it. Function call over. EBP no. Why will EBP move? See, EBP was always there when we did a call. Only EIP moved. Now, okay, now what is EBP? Where is EIP now? EIP is here. No, okay. Harsha Kartikeya. What do you? Why do you? Where did we move EBP when we did a call? We did not, right? Why? Because F did not need a stack frame at all. EBP and ESP be this way. Yeah. So this way, EBP and ESP demarcate the stack frame. Yes. EBP and ESP demarcate the stack frame. EIP somewhere totally different. Call did push to push the current EIP and then move it to wherever it was called. Is that clear, or are there still any doubts?
Okay. Yeah, clear.
Yeah, cool. Now there
So, like
now
in the whole
we
process, we never interfered with the position with EBP.
no, unless and until EBP is written, EBP won't be moved.
Okay. Okay.
There are okay in this entire thing. There are only two things that are moving EBP: this and this. Makes sense, right? This is also not moving EBP. It's just storing its value.
Okay. And then pop EBP is just removing what it stored.
Yes, into and moving EBP back to its original location.
Okay. And which part of it is the return ret?
Ret is below this. G के address में ret is below this.
Okay. So ret only takes care about the EIP part.
Yes, and ESP moves on its own automatically because of that.
Okay. Okay. So like basically, removing the stored EBP is independent of ret. It was something a command previous to it.
Yes, yes, yes.
Okay. Okay. Yeah. Got it.
That's perfect. Sriram, you were saying something.
Yeah, what is the like purpose of moving EBP, like move EBP to ESP? It is to make the G's track frame as the primary thing or something like that, right?
Yes, yes.
Okay.
See, EBP and ESP mark the current stack frame. For that, you need to move EBP to wherever ESP is because that's the beginning of the new stack frame. Here,
Mm. Yeah. Okay.
I have a doubt.
perfect. Go
If
on.
f also involves some of the variables, like then the same thing which happened for G would also be happening for F, right? Like the
Yeah,
EBP would be moving down for F. Again,
yeah.
that would
But
be
as
again happening for G.
yes,
Okay.
yes. That's why we keep storing them, and as we go back, it takes care of
For the
it.
specific case, it doesn't require any variable. That's why we are not like moving the EBP in case of F.
Yes, yes, yes.
Okay,
Because
okay.
it does not
Okay.
require variables,
Yeah,
which
yeah.
is why we do
So
not create its stack frame at all.
yeah, that's what you mean when you don't need a stack for F specifically.
Stack frame for F.
Okay.
Yes, that's right.
Yeah, yeah.
That's perfect. Now you do a ret from G. Okay, G का ret हो गया. G's ret is over. Now because of the way F was written, EIP2 is also a ret. This instruction is also a ret. So this will also do a ret. So what happens now? Who's gonna tell me what happens now? Anyone, just blurt it out. It's fine. There are no wrong answers. You already gave all of them.
ESP moves up, EIP1 is popped.
Yeah, basically EIP1 is popped into EIP. That's it. This ret is over. Now it
And
goes
where is the EIP finally then?
here. After this ret, EIP is here after call F.
Okay, okay, fine, yeah.
Who isn't clear now? Abizar, if you bring up arguments one more time, there are no arguments for now. If you see the functions that I wrote, no argument, no argument, no argument. There are no arguments for now. I will bring them tomorrow or day after or whenever I'm free for the next session and whenever you are clear enough for the next session. I will
Uh,
probably go on.
when main calls F calls G, and G is about to finish, how
Hmm?
does it know what is the next instruction?
You mean after it?
After G's ret,
Yeah. So we stored. So what tracks the instructions? EIP, right?
EIP. Yeah,
Remember we stored EIPs here
yeah.
and later we wrote them back into EIP.
Yeah, how does it come to that point? Like
As
G
in
is the current EIP when G is about to finish is somewhere
uh,
below, right?
somewhere in G. Yes.
Yeah, somewhere in G. How does it move to this position?
See, EIP register is what tells the processor which one has to be done next.
Yeah.
Now, if we change EIP itself,
Okay, so G knows to come to here after it's over.
ret knows.
Yeah,
G
EIP.
doesn't know anything. See, ESP was pointing here, right? At that time,
Yeah,
we take the value that's here. So if okay, one second. ESP was pointing here at that time. We take the value here. Do you see where ESP and EIP2 are?
yeah, but ESP need not be just next, right? It can be like G could have some bigger frame, and it could be like
That
below.
and okay. G's frame got over here.
So when it's over, it's deleted.
Yeah, when it's over, see, the way it works is ret assumes that when the stack frame is over, ESP would be pointing to like EIP2 and ESP would be in this way.
Okay.
That's it.
Okay. How?
What do you mean how? That's how ret is written. Keeping this in mind, ret is written.
Yeah, but how does it? How is the prerequisite for ret come up? Like, how does it happen this before ret is executed?
See, that's how they designed it. Once again, I'm not going into computer architecture.
Okay.
See, I can explain all of that. Please, you are all invited to my 5 hour long guest lecture where all of you will end up crying. There's a very good reason I took a 1.5 hours and not, it became 2 hours in fact. Ret, see, that's to when 5 hour lecture. Bro, I don't think you can do the 5 hour lecture. No, you can't do the 5 hour lecture. Loss only, bro. Loss only. Your loss, not mine. It's fine. Anyways, okay, guys. Coming back. Ret assumes EIP2 is here and ESP is here. After Ret, after another Ret, uh, you aren't allowed. See, I think you are too weak. So the second one. No, you are too weak. You're not stupid. There's no stupidity involved in this. The only thing is too many moving parts. As you can see, a lot of stuff is happening all at once, which Manu is somehow rightly pointing out every single time because he's probably just confused and asking me. So, yes, there are a lot of assumptions, there are a lot of moving parts, and they all come together in this beautiful thing where you somehow manage to get execution. It See, I present it to you in 1.5 hours or 2 hours. It was developed over many years. There was a time when people wrote in assembly and they had no concept of functions. There was a time when people wrote in punch cards. So ret is clear, I assume, Manu, and everyone else who had doubts. Manu, but like, yeah, cool. Peace. That's it for today. Thanks. Now, before you people leave, my very first recommendation, go back, make notes, draw, and understand what's happening. If there are any doubts, there is the group. There is me, there are quads, there are other strategists, there's Mohit, everyone's there. People will be ready to clear your doubts. Please do not hesitate to ask them. I will send this PDF, but I don't think you can understand anything from this at all. I just moved between pages so much. Regardless, I will send this PDF. Any doubts so far, right now, do you have? If you think you can ask them. I believe, what is this note taking app? That's a very good doubt. Uh, cool. So, what I want all of you to do is pick up a pen, pick up a paper, draw, write, understand all at once, and finally make notes. Clear? Once again, any doubts? There any reading material for this? Thorat, I will. Uh, Thorat, Arnav, oh my god. See, this system messes me up. Arnav, I will send you a page. Harsha Kartikeya Vutukuri CS24B075 should have made notes. Yes, I will. This PDF is the reference manual. Arnav, first of all, I will send this PDF. Second of all, I will send you one of my blog posts that should have it. Since you people are so good at OSINT, just find it out. Abizar, that's perfectly right. Stack frames are a social construct. They just got so popular that they got mainstreamed into assembly. You can have one giant ass stack. It's just easier to do it this way. Is there any more doubts that do not involve function arguments? Nope. Glad. Blog post, please. I'll drop. Okay. First of all, my blog does not work on Instinet. So if any of you are in, oh my god, So if any of you are on Insta, you have to use your own you have to use your own internet. This is the link. Scroll down, you should see somewhere, bro. I don't know where it is exactly. To be honest, I don't remember the page. I will find it and drop you the exact link. Basically, it tells you what you need to understand what a processor is, what. I will send this PDF as well. Now, any doubts related to stack frame? Very, very good. I knew somebody would find it. Yep, that's perfect. Okay, so as I said, I lied to all of you. I said only stack and code. There are multiple things as you can see there. They do not matter. As you can see here. Wait a second. What the? Okay, yeah, these are boxes. And it also has arguments. So I think Abizer would be very happy. With this, you can actually understand how arguments are also created on 32-bit. So you also see this leave, right? As it says, it's equivalent to the other two instructions. Since those two were also so popular, they decided to make just one for it. Okay, you are free to leave, but if you want to stay back, talk, ask something, anything, please point. If anything is covered, I will repeat it again and in a more detailed manner, to be honest. Now, do you who wants to stay back? You can leave. Okay, so I am so focused on functional algebra because my project I was looking at EG and they call a C function assembly and they yeah, yeah, perfect. Yeah, somebody raised hand, I guess, or
Yeah.
something.
Can you explain how G collapses and comes to EIP 2 plus 1?
Okay. Mm, can I refer to the blog or should I just do it here? I think doing it here will be better.
Okay, whatever.
Push EBP. So right now, may F. Okay, main. Okay, let's assume main is calling G directly. Since it's just your doubt, Manu, so I'm doing it this way.
Yeah.
Yeah, cool. So call already stored the EIP one. That's clear,
Yeah.
right? This is done by
Yeah.
call.
Yeah. Yeah. Yeah.
Once again, this works because we assume this is how it's working. Basically, it's self-consistent. That's it. So first of all, we haven't executed any of these. This is the stack.